Blah, blah, blah. So I bumped into Scott in the hallway, and he was saying that he was in a classroom last week, and he noticed the screen looked so much brighter than it did in here, and he mentioned it to someone, and they mentioned it to someone, and they got a new screen, new bulb in here, which is why this is like working with the wall wash turned on.
You're welcome.
So, was that you? I thought it might be, because he said, and this person happened to be in IT. Excellent. Thank you. All right, so yeah, we have technology. Oh, really? Okay. That's not bad. All right, so let's talk about the ODP, since it was unreadable until just now. So ODP 241, we are extending our work with tries, and we're going to search a try for a word. So same node structure, and your function is called find word. It takes two arguments. First argument is still the root of the try. Second argument is actually a string. Okay, it's a char star null terminated string in the usual sense. And your function returns a 1 if that word is stored in the try and a 0 if it's not. All right, so how do we do this? I mean, you did this yesterday with your sheets. So here's an example of a try. Right, so suppose you're looking for the word dog. You start at your root, you check the pointer associated with D. You did this in ODP 240. Check the pointer associated with D. Assuming it's not null, follow that to another node. Now check the pointer associated with O. Follow that to another node. Check the pointer associated with G. Follow that to another node. Check the end of string bit, that integer. If it's a 1, then dog is in your try. If it's a 0, or if any of these pointers actually pointed to null, the word's not in your try. Okay, that's the whole search algorithm. So go letter by letter and just keep following links, and what you're doing is you're going down a tree. All right, starting at the root, you follow a link to another node, another node, another node, and then you check the end of string. So you're basically traveling down the tree following. If dog is in there, it's got to be somewhere off the D, somewhere off the O, somewhere off the G, right? And if you look for DOS, you follow the D to here, you follow the O to here, you check the S, and that's null. Right there you can say there's no DOS in here. If you get down here, but this bit is a 0, there's no dog, but presumably there's something else down here that goes somewhere else. So I'm testing your function by passing you the root of a try that I've already built that has some stuff in it. And I'm going to call your function with different words, and your function should do that process to see if the word's in the structure or not, and just return the 1 or the 0. Again, the word is guaranteed to be only uppercase letters A through Z. You can assume ASCII codes. And the root is not null. It's pointing to a structure that has a bunch of stuff in it. So that's just a synopsis of what I just said for how to tell if the node's in there, tell if the word's in there, and there's your test bed. And so this one, I think I made it due tomorrow afternoon at 5. So I'd like you to work on it before class tomorrow. But if you're running into troubles, then we can talk about it in class, right? If you don't start it until 3 o'clock tomorrow and then you try to get help from me, I'm probably not going to be available. So, so start it as if it's due tomorrow morning. And if you get it done early, that's okay. But then if you're stuck, we can talk in class. All right, so questions? I got killed like 80 times on Rogue this morning during breakfast. All right, well, let's, we're going to come back to trees later on after PA4 is done. We'll come back and we'll look at code for balancing trees using the rotations that we described. And then we'll also talk about another kind of balanced tree, which is called a red-black tree. And it's a very different kind of balancing algorithm. It doesn't give you a perfectly balanced tree, but it gives you a tree that's reasonably well balanced. So we'll dig into those in another week or so. But I want to move on to sorting and searching, mainly sorting, and thinking about different sort algorithms. And the general goal of sorting is just to take a set of data and put it into some order. And this could be words that you're alphabetizing, it could be numbers that you're sorting from smallest to largest. Anything can be sorted as long as you have a way to compare two things. So we can use the string compare function with strings to tell which string comes before or after another string. That's enough to sort. We could take binary files and we could sort them by treating them as ridiculously long integers or using some other technique. So we'll mostly stick with just simple small integers for the examples we're doing. Or possibly playing cards, because those are handy for sorting. And so we know at least one kind of sort, which is a bubble sort. And we've used this a few times. We used it in 224 for sorting our dictionary. You've gone over this in 121. So quick review of this, and I want to do a little analysis on it also. Let's take a set of numbers. So the idea of a bubble sort is it's based on making a series of passes through your data. And basically each pass moves one number into its correct position. So each pass moves one number, one more number, into its final position. In bubble sort, think of things in water. Heavy things sink and bubbles rise. We're doing the sinking rock version as opposed to the rising bubble, so this is like a rock sort or something. The idea is, let's make one pass through our data such that the largest number in our data ends up at the bottom of the list. So how do we do that? Well, we could go through and we could just find the largest number and then we could swap it with the last number. But bubble sorts do something a little different. They basically compare each number to the number after it to see if they're in the right order. So the goal we're after is smallest to largest. So start with your first two numbers, see if they're in the right position relative to each other. And 12 should come after 4, 4 should come before 12, so we swap these. So we get a 4 and a 12. And then compare the 12 to the number after it, and that's in the wrong order. So swap those. So this becomes a 3 and a 12. And 12 and 6 are in the wrong order, so swap those. So this becomes a 6 and a 12. And the 12, which was the heaviest thing so far, is working its way towards the bottom. Right? When we get to the 20 is bigger than the 12, so we don't swap. We want the 20 to come after the 12. But the 20 and 5 are in the wrong order, so swap those. 20 and 50, 50 is bigger than 20, so that's fine. 50 is bigger than 11, so those should get swapped. 11 is, or 50 is bigger than 6, so those should get swapped. And 50 is bigger than 8, so those should get swapped. And all kinds of things may have happened up here, right? The 12 got moved around and the 4 got moved up and so on. But the only guarantee is that after we've made this one pass, the largest number in here is going to be sitting at the bottom. So if we make a second pass, we can think of this list as having one fewer elements in it. Right? We don't have to deal with this 50 because we know that's the largest element and it's already in the correct position. So now we have one fewer elements, and we're going to make a pass through this and move the largest thing in here to the bottom, which is going to bring our 20 down to this bottom position. And if we have n elements, if we make n such passes, all n elements should end up in their correct spot. So if you have n items, if we make n passes, we should be fine. And it's actually n minus 1, because once we've got everything up through and including this second number in the correct spot, we know the first number is in the correct spot automatically. But we can make extra passes. If our list is sorted and we make one of these passes, it's not going to do anything. Right, so if you're coding this, you can just say do this n times, and for each pass, go through and do this swapping. So that's basic bubble sort, right? So question is, how many operations do we have to do to sort a set of data? And this codes as usually a pair of loops. So an outer loop where we're doing n passes, and an inner loop where we're doing one pass, which moves the largest number to the bottom of the list. And then inside here, we've got to do some stuff. So how many times are we doing stuff, roughly?
N times? Or n minus 1?
Or, you're on the right track. N squared, right? Because this inner loop is going to execute n times, so we're doing stuff n times. But this whole loop that does stuff n times is itself going to be executed a total of n times. So this is basically order n squared. Now we can improve this. Our inner pass doesn't actually have to process n things. The first time through it has to compare n numbers, but the second time through it only has to deal with n minus 1. The third time through only n minus 2. The second to the last time it only has to compare 2 numbers. So this is basically n plus n. A total of n times. But if we embellish this algorithm a little bit so that we don't go all the way through to the bottom on our inner loop, we're actually doing a total of n plus n minus 1 plus n minus 2. Right, and that's how many operations we're doing, so it's a triangle number. So what do you get when you add the first n integers? You should know this from 215.
N times n minus 1 over 2.
Cool. You did a quick inductive proof, didn't you?
Yeah.
Which is approximately n squared, right? But it's actually n squared minus n over 2. So it's more like order n squared over 2. It's actually a little better than that. But it's only half as bad as n squared, right? So let's look at these orders of complexity. So let me make some fictitious data here. So let's suppose that you have 2 pieces of data and your number of operations is n squared. That's going to take 4 operations. If it's n squared over 2, it's going to take 2 operations. If n is 4, n squared is going to be 16. N squared over 2 is going to be 8. If n is 20, n squared is going to be 400. N squared over 2 is going to be 200. So certainly the number of operations is better here, where it's n squared over 2, than it is here. But in terms of how the complexity of the problem grows, so when we talk about this order, is looking at how the complexity grows. As n increases. So from here to here, n has doubled. The number of operations here has gone up by 4x. The number of operations here has gone up by 4x. From 2 to 20, the size of n has gone up by 10x. The number of operations has gone up by 100x. And over here in the n squared over 2 case, the number of operations has also gone up by 100x. And this is what big O notation is trying to capture. The fact that when you double the amount of data, your time to operate goes up by 4x. When you increase the amount of data by 10, the time to operate goes up by 100. And that increase is the same whether the number of operations is n squared or n squared divided by 2. So this is why we say that these are the same thing. Right? An order of n squared algorithm is basically the same as an order n squared over 2 algorithm. We're not saying they take the same amount of time. We're saying the time that they require increases by the same factor when you increase n by a certain factor. So we throw away constants when we do this big O notation. And we're also looking kind of asymptotically. If I try to do a bubble sort on something with 1 piece of data, it's going to take a lot of time doing input and output in the beginning, initializing variables, allocating space for arrays, all that kind of stuff. It's not going to take exactly, 1/10 what it would take to do a larger set of n, right? But asymptotically, as n gets really, really big, this n squared or n squared over 2 becomes the dominant term. Yeah?
This is kind of like when we take a look at limits at infinity, right?
Yes.
We kind of ignore any of the non-linear terms.
Exactly. Right, which is why when we have order n squared minus n over 2, that minus n part is going to become less and less important as n gets big. So usually when we write a big O, if it's a polynomial, we're just going to use the leading term. If there's a constant, we're just going to reduce that constant to 1. And so you'll see things like order n squared, order log n, order n times log n, order 1, things like that. We can also speed up this bubble sort by each time that we make a pass, noting if we actually swapped anything or not. Because if our data is sorted to begin with and we move through and our inner pass doesn't do any swaps, we don't have to do any more passes. Nothing different is going to happen. So we can set a flag in here every time that we do a swap, and we can replace this outer loop with a while that flag is set. And now it'll only go through as many passes as we need. So best case, you start with a thing that's perfectly sorted, it makes one pass and it's done. Worst case is probably when it's completely sorted in the reverse order and it's got to do a full n passes, and average case is somewhere in between. We typically look for average case when we're talking about big O in here. So those kinds of embellishments don't change bubble sort from being an n squared algorithm. Alright, so you know bubble sort, you've coded bubble sort. Remember, bubble sort is order n squared. Okay, and that's kind of our starting point for sorts. So there's two other versions of order n squared sorts that are not bad to code up, but they're really hard to keep straight. So there's a selection sort, and there's an insertion sort. And you gotta find a way to keep these straight. Put them on your notes or something. These are both order n squared. And we start with a bunch of numbers. So we're going to go ace through 9, and then jack, queen, king is the sort order. And let's say we want to sort from smallest to largest. So I want the ace on the top, I want the king on the bottom. Okay, so two fundamentally different approaches to this. And the name of the sort is determined by where we're actually doing the sorting action. So in a selection sort, what we do is we choose the smallest element. We add it to the output. And we go back and we choose the next smallest element and we add it to the output, and so on. Okay, so what does this look like? We're going to go through our input and we're going to find the smallest number. So smallest number is 8. 9 is bigger, so 8 is still smallest. 8 is still smallest. 2 is smaller, so that's our smallest number. 4 is bigger, 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 bigger. There's an ace, so ace is the smallest element. There's a jack, queen, king, and a 7. So ace is the smallest element. Okay, so we're going to take that, we're going to put it in our output pile. Getting fancy on you here. Bam. Alright, so ace goes in our output pile. Then we go back to the top. We go through our input and we pick the smallest element. And what's the smallest element? There's a 2, which is smaller. That's the smallest element. So we take the 2, and we add that to our output pile. My pile's going to be backwards. That's okay. And then we go through and we pick the smallest element. Looks like a 4, looks like a 3. Yep, 3 is the smallest, and we put that in. Okay, there's nothing magic going on here. We just make a series of passes. Each pass we pick out the smallest element and we put it on our output. There's our 5. Smallest element is a 6. Right. There's a 7. Go through. There's an 8. There's a 9. There's a 10. There's a jack. There's a queen. There's a king. And we're done. Yay! I didn't mess up. Alright, so that's a selection sort. And insertion sort, what we do is we choose the first element and we insert into the proper place in the output. Alright, so we just grab the first element off the top. That's an 8. and we put it into our output pile in the proper place. Well, there's nothing in our output pile, so we just put it there. Grab the first element in our input, that's a 3, put it in the proper place in our output. Well, it should come before an 8, so it goes right there. Okay, grab the first element, that's a 2, put it in the proper place in the output. It should come before an 8, before a 3, it should go right there. Grab the first element, put it in the proper place, that should go after the 9, after the 8. Grab the first element, put it in the proper place, 2, 3 should go after the 3. Right, and we keep doing this. So we're always selecting the first card in our input, but we're placing it not just on top of the output pile, but in the proper location in the output pile so that the output remains sorted. So that goes right between the 5 and the 7. And there you go.
So it's like a queue of inputs inserting into the list.
Yeah, you could do that, definitely. He said it, not me. All right, so selection sort. So for I equals 1 to n, you have to do this for each card that you're going to add to the output. So if you have n numbers you're trying to sort, you're going to have to do a total of n passes, right? And in each pass, you're going to pick the smallest element. And then in an inner loop, we need to just add to the output array. Right, so it's an order n operation to find the smallest element, because you have to go through and remember 8's the smallest, and then see if 9 is smaller, and Jack, 10, Queen, get to a 7, say 7 is smaller. Do this whole thing, and when you're done with all n cards that you've looked at, all n inputs, you'll know what the smallest number is. So it takes n operations to pick the smallest element. Adding that to the output is just copying it to the bottom of an array, okay, or putting it on the back of a list. So that's an order 1. But then this whole thing has to happen n times. Because each time you do this inner loop, you end up with one more card on the output. You have n things that you're trying to sort. So you're going to have to do a total of n passes. And so this is going to be order n squared. For an insertion sort, you pick the first element. Well, that's an order 1 operation. Just grab the last element in the array, for example. But then you have to insert it into the proper place in the output. So if this is what my output deck looks like, I have to move through here until I find a number that's bigger than this and then put it in right before. This is your linked list insert, right? So this insert is an order n, and you have to do this a total of n times. So this is going to be an order n squared also. So bubble sort, selection sort, insertion sort, they're all basically the same complexity in terms of time. Slightly different in terms of implementation, though. So back in the 60s, before hard drives were a thing, data was stored on magnetic tape. So if you watch old sci-fi movies, there's those reels of tape that like move back and forth in the computers, right? And you could store a lot of data like this. So you'd have, you know, a few thousand feet of magnetic tape, and you magnetize it ones and zeros, right? There's a real bad downside to magnetic tape, though, which is you can't just automatically go to some location in the middle of the tape. If I'm sitting at the beginning of the tape and I want a piece of data that's in the middle of the tape, I have to spin that tape all the way onto this reel until I get halfway through it, and then I can read my 2 bits of information that I want. Now I want something that's back in the beginning of the tape. I got to spin the tape back over there and get back to the beginning, right? It's really, really bad for random access. Disk drives are not as bad. You still have to spin the platter until the thing you want gets under the read-write head. But we have multiple cylinders, right? So at most you need to make one revolution, 7,200 RPM. It's not too long, it's 120th of a second. And memory is, you know, better because you can just go to an arbitrary location and read what's stored there, and you don't have to wait for medium to move. So if you imagine a world where you don't have this kind of random access to data and you start trying to do some sorts, that changes the way that you're going to do your sorting. A selection sort, I need to choose the smallest element and add it to the output. Well, that means moving through my tape from beginning to end to find the smallest element. Bubblesort, you're moving through from beginning to end, but you're always swapping 2 things that are close to each other, right? I never need to sort of pick up a number and move it to the end of the tape. I'm kind of swapping them as I go through. And so depending on what your physical medium is, some types of sorts will make more sense than others. We don't have to worry about that anymore because we got fast stuff, relatively speaking.
Actually, like, there's a shortage of that magnetic tape now.
Is there really?
Recently, like, someone was trying to create a fun little set of, like, mass-produced cassette tapes again, and like
cool.
The vinyl craze going back.
Yeah.
So like now going to cassettes for a retro feel, and like a lot of times it's just not possible because the massive like quantity you want.
Yeah.
Produced.
Interesting. Yeah.
I saw a site selling like 150 terabyte like magnetic tape drives.
Yeah,
for,
nice.
Business use.
Yeah, they were definitely impressive. And I mean, you would have a rack filled with tapes, and if you wanted something, you just go grab the tape and put it on your machine. So you got to play part of the role of the operating system, which is kind of cool. We also discovered at one point, company I was in, that the fastest way to do backups was to write things to mag tape, stick them on a FedEx truck, and ship them to another part of the state. It was faster than what we could do over the internet at the time, just for the amount of data that we had. So sometimes old technology is good. All right, so you can code these up, right? There's not a whole lot of mystery to how you code these. Selection sort, so presumably we're starting with our data in an array, and we have something that indicates how much data we have, so something that says how many elements we have in the array. So let's make some numbers. So this is selection sort. So selection sort, we want to find the smallest element, say. So let's call this data. So clean way to find the smallest element in an array: seed your smallest value to, say, the first element in your array, and then loop through the remaining elements, right? Don't just set it to -999 or something like that, because those things always come back to haunt you. So set your smallest variable to the first element, and then loop through the remaining elements, and if data I is less than smallest, Set your smallest equal to that element. And when you're done, smallest is the smallest element in there. So output bracket out index plus plus equals smallest. So start off some output index at 0, and here's your output array. So pick the smallest element, put it in location 0, increment out index, loop through again, find the smallest element, put it in your output index 1, loop through, find your next smallest, put it in out index 2, and so on. And when you're done, your output array has your sorted numbers. But there's this business of choose the smallest element, add it to the output. We don't want to choose that smallest element next time we go through. We want to somehow know that we've already taken that element. We want actually the next smallest element. And the way this is written, every time we go through, we're going to end up picking the same smallest element. So you got some options. You can set a flag. So make these composite pieces of data that have a flag saying whether you've already selected a number. And before you do this check, make sure you're checking a number that hasn't been selected, and if it's the smallest, go ahead and set that flag. In which case you need to remember what that smallest index was, so that when you're done, we can say something like clear flag at that location. Or you could put in some really large value so that that's never the smallest, and that's a little quirky maybe, but you can go through and find the largest number and then just store that plus 1. Or if this is a linked list, you can just remove your number from the list, and that's a nice and clean solution. And we don't need this to be sorted, or we don't need to go in the middle of it, so we can always make a linked list work well. But again, you need to know where that smallest number is, so that after you found the smallest, you can go back and delete it from the list. So you have to save a pointer to the previous node or something. So there's a little bit of detail in there, but none of that changes the order of complexity. So the other thing on big O notation that I should have made clear, when we calculate big O and we say we're doing n squared operations, right, this do stuff could be swap two numbers in an array. It could be do 10 million operations. Okay, this little do stuff might be short, or it might be very, very long. But we're doing roughly n squared of this, whatever this do stuff is, in the middle. Right, now if this is a linked list and we need to allocate nodes to put something in the output, and we need to save the previous node and then go back and adjust the pointers and all that, that's more complex than swapping two elements in an array, which is like 3 assignment statements. But the order of complexity doesn't change. Okay, it's still order n squared. But if we're doing a lot of stuff here, it might be order, 500 times n squared compared to a bubble sort. But remember, the constants don't affect us. 500 n squared is still order n squared. So we can safely, wave our hands and say we're going to do 25 million things in here and still say it's order n squared. So it's not bad to code, you just have to sort of deal with how to remove elements so you don't count them again. Insertion sort, remember we're going through and we're just picking the first element in our input, so that's easy. We just, for I equals 0 to n, we take element I from our input array and we move it to our output, but we put it in the correct spot in the output. And so we move through our output, we find the first place to insert it. Well, if it's a linked list, we've already done that. We make a new node, we sandwich it in between the previous node and the node that's bigger. if it's an array and we want to insert our number right here, we may have to move everything down. But that inner loop is still order n, right? It takes some number of operations to find where we want to insert and then some number of operations to move everything down. And the further we have to search to find the insert point, the fewer operations we have to do to make space for it. And if we're inserting the beginning, that took one operation, but then we have to do n-1 moves to make space for it. But it still ends up being order n. And there's lots of fancy versions of selection sort and insert sort that do things like let you use a single array instead of having an output array and an input array. And so it kind of sorts the array in place. There's things that minimize how much you move data around, because even though we have random access memory, it still kind of penalizes us like the old magnetic tapes. If we bounce around from one location to another in memory, we pay a performance penalty. Because there's this notion of caching, and caching is built on the idea that data is accessed locally. If you access one location in memory, it's banking on the fact that your next few accesses are going to be physically close to that first access in memory. And if you read memory from all over the place, over here, over there, off in Timbuktu, and you just do all these random reads from different locations, it's a lot slower, because you basically short circuit the caching system. So there's versions of these sorts that do things like go through your input or your output without moving your data around too much physically. So trying to keep things local, trying to capitalize on cache. Okay, so those are our main n-squared sorts. So bubble sort, selection sort, insertion sort. And selection, insertion, remember the name is based on where you're doing the sorting. Selection sort, you're basically sorting by which numbers you select from your input. Insertion sort, you're sorting by where you put your numbers in the output, where you insert them. And bubble sort is just bubble sort. Okay, so those are n squared. What's the best sort we can do? Theoretically.
Order 1.
Order 1 would be pretty nice. Order 0 would be even better. Order 0, everything would always be sorted. I don't know if that's possible. But if you had some way to somehow live in a world where your data was always sorted, I don't know if you lose the ability to do anything or not. But if you never had to sort anything, that would kind of be order 0. But order 1 is certainly imaginable, at least, where no matter how much data, it takes the same amount of time to sort it. Is that achievable?
It depends on what information you're working with, as well as what data type it's stored as.
Definitely.
And also the capability of your machine is if you can only sort 2 numbers at a time, it'll have a limit to how much those data it can sort.
I'd agree with that.
Hypothetically, if there's a machine that can sort any number of data in just one move, that'll be just one pass.
Okay. What would a machine like that look like?
I don't know.
Where do I buy it? Buy it from a hypothetical store. Let me give you something to think about. So, here's a tub, swimming pool, something, and it's filled with oil. So something thicker than water. And you have a series of rocks of different diameters. And simultaneously you drop them all into this pool of oil and they begin to sink. And let's say they all weigh the same, but they have different surface areas. the first rock to hit the bottom is going to be the one with the smallest surface area. The next rock's going to be the one with the next smallest surface area. The last one to hit's going to be the one with the biggest surface area, the cross-sectional area, right? And I can do this with my 6 rocks here. I could do it with 6 million rocks. And if I just look at the order in which these rocks hit, it's always sorted. And it's independent of how many rocks I have, right? The time it takes to do this sort is basically a function of how long it takes the biggest rock to fall. So if all my numbers are smaller than or equal to this, right, I can have a million different sizes in here, and I get them sorted in the same amount of time. And it's almost like some kind of weird order 1 sort, right? And it's playing off parallelism of physical systems. I don't know how to do that in code quite, but it's a suggestion of an existence proof at least. Then maybe there's an order 1 sort algorithm.
What do you do if you add a new rock after you already dropped all?
No, you guys have them all in the beginning. Otherwise,
All the rocks up again.
yeah. Otherwise, you say we'll sort you in the next experiment.
I mean, doesn't that, like what he said about, oh, well, what if you had a new rock, that you have to have all the rocks at the start, just like shows that there's no sorting algorithm, so that's like the magic hammer you use to hit every nail.
Right, right. This is true. All right, so we'll talk about merge sort tomorrow, which is going to be a recursive sort. And merge sorts are awesome.